So in this video, we look at one of our oxidation reactions, and this is specifically the PCC oxidation. The PCC oxidation is different from the Jones oxidation in that it's a very, very mild oxidant. So whereas Jones reagent often runs the risk of over-oxidation, especially with primary alcohols, under Jones condition, primary alcohols typically get oxidized all the way to carboxylic acids. PCC is only going to take us to the aldehyde or ketone. PCC is an oxidant. Among the reactions we learn in an intro organic course, this is definitely one of the newer ones. Its discovery is credited to E.J. Corey in the mid-70s. And again, it's a much more mild type of oxidation. So with a secondary alcohol, like cyclohexanol here, we can easily form ketones. But as we said a moment ago, the big difference is if we were using Jones reagent will oxidize a secondary alcohol to a ketone, just like PCC does. But with Jones reagent, a primary alcohol gets oxidized all the way to a carboxylic acid. With PCC, we get to the aldehyde and the reaction stops there. So it allows us a much higher level of control on this reaction. And so by looking at the mechanism, and we can get into first of all how this reaction works, but we can also then talk about why does the PCC oxidation stop at this point. So the PCC, pyridinium chlorochromate, does have a positively charged pyridinium cation, counterion. We're not going to show that here because it doesn't really play a role in most of the mechanism. But the reaction starts with the alcohol attacking chromium and shifting electrons up onto oxygen. In many ways, very much like the way a nucleophile attacks a carbonyl. Which gives us this intermediate, where one of these oxygens adds in its lone pair, reforms the double bond, and kicks out chlorine. We lose the proton on that positively charged oxygen. And that sets us up for our final step, which is anything that can function as a base that's present, whether it's the chloride we just kicked out or anything else in the solution that can function as a base, come in, remove this hydrogen, electrons shift down, and we kick out the chromium group. This gives us the aldehyde, and in the case of the PCC oxidation, the reaction stops here. Why doesn't it keep going, whereas the Jones oxidation did? The main issue here is that with the Jones oxidation, we need sulfuric acid. When you have sulfuric acid in the presence of an aldehyde, you form the hydrate. The hydrate is able to then be oxidized further. PCC, there's no strong acid present, and because there's no strong acid, the reaction stops at this point. So where might we run into an oxidation like this? So maybe two of the most important examples, and they're not PCC oxidations, but they are oxidations in the exact same type and category, are found here in the citric acid cycle. And where can we find them? Well, for example, isocitrate, we can see here, has a secondary alcohol that in the presence of NAD+, we oxidize to a ketone. And later on, malate has its secondary alcohol, which can be oxidized to a ketone. So oxidation reactions of alcohols, very, very important reactions, not just synthetically, but also within biological systems.